What's up everyone, and welcome to another video of programming for data analytics 2. Today we're going to continue on the cryptocurrency data sets. Now that you have seen how support vector machines work in the previous videos, we want to apply support vector machines into the crypto data set. And also, now that you've seen a couple of the machine learning algorithms, I can just show you how easy it is to apply other ones. So we're going to actually also go in and apply decision trees and do ensemble learning with random forest. But you could apply any of the machine learning models that are available in scikit-learn in the same way. It's all following a pattern. So by the end of this, you'll see that it's very easy to go in. And even though we haven't done any neural network videos yet, you could do a neural network almost the same way too. So very cool stuff. So let's just jump right in. So here we have the code from the previous videos where we were trying to predict whether the Ethereum price was going to go up or down using the Bitcoin price. And then we also have the code from another video where we did logistic regression, where we said if the price is merely going to just go up or down. So instead of trying to predict the actual price that is going to be, we're just trying to predict the trend if it's going to go up, well, technically up or not, which, you know, because I guess down and basically flat would be the same thing in our case. We have just two groups, up and down. And so one of them is regression and the other one is classification problem. And so support vector machines are typically used for classification. However, there is a regression version of a support vector machine, which we call support vector machine regressor. And so we're going to try to apply support vector machines both for classification and regression with our crypto code. So what we're going to do is we are just going to, let's go ahead and start with the, let's start with the up and down, since that's more of the classical one, right? So support vector machines are classically used for classification. So we start by just copying the code from the previous lecture that we have. And so we're going to label this as support vector machine classification. And so what I want to do is I want to go look at the documentation. So this is the documentation from scikit-learn's website for support vector machines, particularly for classification. So you can see here, see support vector classification. This implementation is based on the libSPM. So if you saw the previous videos, I did talk about the libSPM library and how that's kind of like the OG library that scikit-learn then takes and sort of, brings to the rest of the world by sort of fitting into that cookie cutter mold of like, this is how machine learning libraries work. And it's great that they do that because, like I said, today we're going to be applying 3 different machine learning algorithms in one video. And you'll see that the pattern is the same. And that's because they molded it that way. So, you have your model function, your fit function, your predict function, all that works the same. However, you're more than welcome to go in and explore doing this using libSPM directly. So we can see that just like any of the other models, we have parameters. The big thing with support vector machines is the kernel function. You want to play around with that and see what works best for you. Obviously, there's a lot of math behind which one should work best for you. And in the ideal case, you would understand the math. But if you're just trying to get some machine learning up and running, some data science and quick data analytics, then you can just leave the default of the RBF or play around and just literally just swap them and see what happens too. I mean, there's no crime in doing that. It's a crime if you don't use these tools when they're so amazing. So yeah, and the same goes for most of the other parameters. You can go ahead and read about it and get an idea from what they say. The only one that I do encourage you to use is the random state, because like, I said in the past, when you're doing machine learning, you kind of just throw a dart at the wall, right? And that's your initial sort of like estimate for your weights. And so then, it starts looking for that local minima. So you could think of it like you're throwing it at a little like U shape and it just kind of bounces until it settles on the bottom. But actually, it's picture time. So, you could think of like your weight or your loss function. This is what it looks like. This is the global minima. That's what you want. That's the one that's like the least amount of error. And then I guess this would be like the worst amount of error per se, assuming this. And so when you throw the dart, so throw a dart and it hits right here. Where's it going to go? Well, it's going to kind of bounce around here and just stay here. If you're lucky, it might kind of go and bounce more, but it's probably just going to get stuck here. And this is the local minimum, right? So like that's what your model is going to say is the best thing. Obviously, there are things you can do to models to avoid this kind of issue, but it's always a sort of a overarching problem. And so the next time you throw a dart, it might hit here. And so you might end up with this local minima, which is much better than this one. So your algorithm or your model in this case is going to perform better. You get higher accuracy, or you'll get a smaller mean square error or something. Another time you might get really lucky and you might throw it like here. So it actually reaches the global minima, and this is like the best case scenario. So when you're trying to present your model to others and say, hey, I came up with this really beautiful model and it works a lot, it like works really well. Sure, but like, does it really work like what you did? Did you just get lucky with that specific model, or is your implementation of this like something that can be reproduced regardless of where you start that sort of guess? And so you want to make sure that you're not intentionally finessing this. So you want to know where your first dart hit. And even though it's a random throw, you want it to be the same random throw. It kind of it shows honesty in what you're doing to make sure that you're not gaming the system. So there is you know, if you do get lucky, you should be happy about that. But it's a lot harder to trying to improve your own model if you just keep bouncing around, because like what you did to change it, did it actually help it, or did you just get lucky in that throw? Like, hey, I'm going to throw my dart and I get this minima here. And then I'm like, maybe I can improve it. So I tweak it, and then I throw my dart again, and it just happens that I hit this minima. And what I tweaked actually didn't matter. To me, it might look like what I tweaked actually affected it negatively. And then if I tweak it again and I get this one, and it just happens to be because I hit this dart over here, again, I might think that what I modified actually made it better when it was just merely like RNG. So if you keep this dart in the same spot, let's say there, and then you tweak things and then you see it actually improve, then you know it's not luck. It's actually what you're doing to improve it. So that's another big case for doing that. So I've said that in the past videos, but it's always good to emphasize those things because they're important. Okay, so this is what we're going to do. As always, scikit-learn does have examples at the bottom, and I encourage you to kind of take a look at these to kind of understand how it works. You can see here that they're just throwing in some data. You can see that we do need to import this SBC, and we need to import these two functions here. And once we do that, we can go ahead and make the model. We can fit it, so we can train it, and then we're good to go. We can predict with it and whatnot. So this is what will kind of tell you what you need to do to modify your code to go from using logistic regression, which is what we're doing right now, to using support vector machines. So let's go ahead and do that. So the first thing that we need to do is we need to import those two functions that are there. So the pipeline and the pre-processing. So I'm going to go ahead and scroll down here to where we actually imported the logistic regression model. Like I said, if you want to refresh this code, just go ahead and rewatch that video. Here we go, create linear regression object. So I guess now this is going to be a support vector machine, right? So we'll change the labeling there. So we're going to import those two models, or sorry, those two functions. And then instead of importing a linear model, well, I'm going to import a support vector machine, right? So import SPM, support vector machine. Voila, that's as easy as that. All that is left now is for me to actually go in here and you know, like decide on a specific support vector machine model that I want. So delete the linear model that we had. So let's delete this one, and then let's do SPM dot. And you can see there's a couple of different things you can do here. If you remember from the live SPM video, there are the discussion on what the different things of these are, but you can also just highlight them and look at documentation. We can see here we have a support vector classification, so that's your classification problem. We have the regressor, so that was for regression, so we'll use that later. And we have another one for classification and for regression. One class SPM is also classification, and then we got another one for regression. Okay, so for now, let's go ahead and start with just the linear one, and then leave their same random state, and then we can get rid of the solver and the iteration stuff, because that was, you know, for the linear regression model, those parameters. We can definitely go in here and pass in a different kernel function and other things. But for now, let's just try it with the default settings and see what happens, okay? So actually, before I change it, I want to remember what I got, right? So let's just make sure that I actually have the old values. Let me undo this, actually, at least until there. It's fine that I import this. It's not going to affect it. And let's just run this. Okay, and let's write these down. So here we have the classification problem. These are our confusion matrix outputs. So the way I'm going to compare it is I'm going to mostly be looking at precision and recall, but I can also look at the accuracy. So I'm just going to take these and I'm going to just put them here and labeled it. So I'm going to say this is my logistic regression, or classification, in other words, binary classification. And what was the accuracy? Let's save the test one. The train one doesn't really tell me much, because I could be overfitting. So now that we have this, we can actually go in here and import the SPM. Okay, and then let's remove these. Like I said, we don't really need them. And we also are probably gonna have to remove this coefficient one, because I don't think the SPM has that function in there. Well, here, let's just run it and get the error, because I don't remember what line it is. Oh, no, actually we didn't get an error, actually. Never mind. I thought we would get an error with the coefficient function, but it's fine. Okay, great. So we'll just run it one more time to make sure that I was in luck. Yeah, so, okay, so let's take a look at the results. So we can see that the accuracy is around the same. So let's actually also save these. So I'm going to go in here and I'm going to say SVM classification. I'm going to save the accuracy, and I'm going to save the precision and recall. So what we can see from the start is that while the accuracy is about the same, I mean, it's like, you know, slightly like less than 1% lower, the precision and recall changed. In fact, I would say they kind of flipped around. Let me see if I can make this bigger. There we go. It's better. So we can see that the while the accuracy remains around the 77% line, the recall went down from 83% to about 59%, and then the precision went up. So we flipped it. So let's remember precision and recall and kind of understand what that's doing, right? So if we run it again, and we can see our chart here, you know, we can see that we have just a few false positives now, right? And if you remember precision and recall, so let me pull that up. Recall. Actually, here I have it here. So if we go up and look at precision and recall, so we can see that precision is going to be true positives divided by true positive plus false positives, right? So the more false positives we have, the lower our precision is. The more false negatives that we have, the lower our recall is. Now, when do we not want false positives? Well, remember, this is like a financial data per se. So a false positive means that our algorithm is saying like the price is going to go up, but it actually didn't go up, right? And so if we think the price is going to go up and we go in and buy Ethereum and it goes down, then we lose money, right? So we don't want false positives. Now, what's a false negative? A false negative is basically when our algorithm says, hey, I don't think the price is going to go up, so like don't buy. And then the price actually ends up going up anyways. And that's kind of like a missed opportunity because you could have bought Ethereum that day and made some money, right? So in our case, that's not too bad. I mean, obviously it's lost profit, But I would rather have an algorithm that has no false positives, so you're never buying a mistake, and then have a couple of false negatives where like the algorithm was being kind of conservative, like, hey, you could have bought, but like, I told you not to buy and it went up, but oh well, you didn't gain money, but you didn't lose money, right? So in our cases, we want to reduce false positives. The other example I gave in the other video was with medical tests. That's the other side of the coin. With a medical test, like say a COVID-19 test or like an HIV test or something, you want to have the lowest amount of false negatives possible, right? Because a false negative is going to basically say, hey, you don't actually have the disease. You don't have COVID, but you actually do. And that's really bad because now you think you're safe and you go out there and super spread when you actually had it, right? However, a false positive, while bad, is not too bad because a false positive says, hey, I think you have COVID, and you're like, oh gosh, okay, maybe I should play it safe. And even if you don't, then I guess worst case scenario is you just got a little scared. But you can always take another test and then, confirm, right? That's what they tell you. So in this scenario, it's much, much worse to have a false negative because that's basically someone going along with their day, thinking they're okay when they're not. Whereas with the financial data, a false negative was like, oh, I didn't invest, big deal, whatever. With the medical one, it's a big deal, right? On the other hand, the false positive with the medical one is like, whatever. I mean, you don't get me wrong. You don't want to have false positives, but like if you're trying to give and take, you'd rather have false positives than false negatives because that just tells you that you're just a little bit too sensitive. So it's like giving everybody positives per se. Whereas with the medical stuff, or sorry, with the financial stuff, false positive is a big deal because you're buying when you shouldn't. Okay, so those are the two, those are just two examples where like we have complete opposite sides of the coin, right? One of them, in the case of the financial one, you want your precision to be really high because you want to reduce the false positives. And in the medical side, you want your recall to be really high because you want to reduce your false negatives, right? So with that in mind, let's go and take a look at this. So we can see that our precision went up, right? That means that we have less false positives. That's good for us in this case. Support vector machines are giving us a better model. The accuracy remains the same, but the precision went up. Now, that went up at the cost of recall. The recall went down from 83% to 59%. What does that mean? That means we're getting more false negatives, which in our case, we can live with. What that's really telling me, like as an overarching, is that the support vector machine is a more conservative algorithm, meaning that like it only buys when it's sure the price is going to go up, and it makes less mistakes of buying when it shouldn't. The accuracy didn't go up. In fact, it went slightly down. So you might say, oh, the support vector machine one's worse. But again, the accuracy doesn't tell the full story, right? We take a look at precision and recall, and that tells us better. And of course, this is supported by the graph. You can see that the false positives are much, much less than before. And, or actually, yeah, and then the false negatives over here. You have quite a bit more because it's more conservative. In fact, let me take a screenshot. Hopefully that doesn't break the lecture. So here's a screenshot of this. And then let me rerun. I guess I have it here, right? Yeah, so this is the logistic one. So rerun the logistic one. So this is logistic regression, and then this one's the support vector machines. You can see how we have more false positives in the support vector in the logistic one and less in the support vector machine, and then it should be the opposite over here. Interesting. It's it's like I feel like there's so few false positives. It's almost like not making a mistake, right? Whereas here it just looks like there's less, but not that many less. So that's interesting. The true positives and true negatives look about the same in my eyes. But like again, You don't need to see the graphs. You can just read the numbers. And you can look at the confusion matrix too, right? So, yeah, I mean, I'm not saying support vector machines are always going to be better, but in this case, they were. And that's just using the default one. We could probably squeeze better, like more, you know, more juice or more like precision or recall out of this if we tweak around the parameters quite a bit. But again, this is just kind of showing you that you can use other machine learning models very, very easily. I mean, look how far we're in the video, and we already try something completely new. So, yeah, I think that's all I'll say about that. Let's maybe let's try this here. So instead of just using this linear SBC, let's try using the make pipeline and see what happens with that one. So because if you remember from the from here, you have your make pipeline, right? And we're not doing this make pipeline. We're not actually doing the way this said. I just kind of imported that. So let's try that one and let's see how that one does. Okay. So make pipeline, standard scalar. So I'm just copying the code from the example SBC, which we need to do SPM.SBC. And then let's stick with gamma auto. So the same parameters that they show. Yep. And then just try that one. Let's see how that one does, okay? All right, so this one, wow, it really flipped it. So let's just keep writing them down here. So this one is using the SBC scikit-learn example, okay? So that one, look at that. The recall went super high, but the accuracy overall, or in the test data set, like really took a dive. So initially this might look nice, but it's not really. The 98% recall means we have basically no false negatives, meaning that, but the fact that we have a really low precision of half, which is like almost like flipping a coin, this is telling me this algorithm is like the YOLO algorithm. It's just like it just goes and buys like every single time. It never stops. The fact that there are just yeah, like because it has a bunch of false positives, which is what's lowering this. So it's buying when it shouldn't, and the fact that it's never missing a buying opportunity because there's no false negatives means that it's just always buying. And we can see that if we look at this. We have only 3 false negatives. The ones in the corner, you can't see it. And then we have very few true negatives as well. But you can see it's just always buying. It's just always like the algorithm is basically just buying every single time. So this one's pretty bad, I would say. But that's fine. I wanted to try it out. Let's try tweaking this one though and changing the kernel function. So let's go ahead and put a comma here, bring it to the next line, and let's change that. So right now it's probably using the default, which is RBF. So let's put that in and just confirm, see if we get the same value. Well, we're not using random states, so it's probably gonna change a little bit, but it's about the same. Yeah, so let's go ahead and switch this to using the sigmoid kernel function, okay? See how that does. So that actually still has a pretty weak accuracy of 56%, but at least the precision and recall, actually the precision is still bad and the recall is just bad now too. So this is actually the worst one we've seen so far. Yeah, actually that is pretty bad. So yeah, so you can see that the linear one worked much better than these ones. So yeah, let's leave that one in here. That was the winner of the support vector machines, right? You can see that yeah, that's much nicer. Okay. So yeah, that's all I want to say about that one. So let's move on. We have a lot to go over, right? So that was the classification problem. Let's do the regression problem, okay? So we're going to take the code from the regression, one linear regression. And so now we're going to use support vector machines, or better yet, support vector regression, I suppose, right? So let us go and refer to the documentation. So that's this one right here. SBR, epsilon support vector regression, and pre-parameter in the model are C and epsilon. And this is also based on libSVM, which is the library for support vector machines that is kind of brought in here. And you can see that, you also got your kernels, and there's probably some sample code here. So we can see that it's the same thing. The make pipeline, the SBR, the epsilon parameters, and then there's no kernel or anything here, but you could manually set it. You can see the default is doing RBF. The C and the epsilon are here. If you want to know what they are, is a regularization parameter. The strength of the regularization is inversely proportional to C, must be positive. The penalty is the square of the penalty. So if you want to know more about this, you have to look at the libSVM library and understand these better. Same with the epsilon one, okay? So you can just read the documentation and understand that. But the thing is, I want to show you just how to use them quickly, right? And start tweaking them. So you can see it's going to be just as easy as the other example. So now that we put in support vector machines in here, let's go down to the part where we actually import the model. So right here, okay? So just like the previous one, we are going to want to use the make pipeline and scalar. So I'm going to bring them in here. And then let's change this to support vector regression. Support vector machines, typically used for classification, but you can use them for regression if you want, and it is available. I'm not holding my, not having very high hopes that this will do good, but we'll see. And just because you find fancy machine learning algorithms doesn't mean they're going to do better than your good old regression or your good old classification, the bread and butter machine learning. So don't just think like, hey, I'm just because support vector machine sounds fancier and it's newer than the regression, than like logistic regression, that is going to be better. There are some cases where it's better, out there, but it's not always just going to be just the case by automatically. Same even goes for things. I'll even go and say the same goes for things like even deep learning. It's not always going to win. You have to understand when to use the right models. So, okay. So we're going to import SPMs into this. And, okay, let's see. Let's just take, I'm just looking at this. Let's just bring in this line as is right here. Make pipeline sender scalar epsilon 2. Okay, and then go from there. So make pipeline sender scalar. And by the way, we could improve our, I will talk about what else we could do other than changing the model to improve the results in a bit. For now, I just want to show you first, okay? You can use different models. Epsilon from 2, so I'm just using the ones that they use there for now. We can tweak those later. But yeah, just put those in, and yeah, we should be set. Oh wait, no. Well, we're gonna get that coefficient error probably this time. Yep. Or wait, actually, what? Oh, SBR is not. SPM.SBR, because SBR is part of the SPM class per se. And then just comment out the coefficients one, because that's not it's not part of what you get back from there for the metrics. Okay, here we go. So you can check the video from or here actually. Let's again, let's rerun the linear regression one so I can save the I guess in this case the mean square errors. So this is linear regression one right there. And then let's save the save these three. I mean, one of them is just, you know, the square root, but you know, it's easier to copy paste. Okay, so let's do linear regression down here and just put them there. All right, so now that we have them there, let's go ahead and run the support vector machine. There's our picture. And let's take a look at these. So let me just copy them and put them here. So support vector machine, or support SVR technically, support vector regression. Let's take a look. So we can see that it's actually worse. So whereas before we had a root mean square error of 29, now we have 648. And our mean absolute error used to be 15 and now it's 307. So it's actually performing worse than before. Probably we could tweak around these parameters and see if we can improve it. But just off the bat, you can see that it's not quite as good as you would hope. How did we have it before? Oh, this logistic. I wonder if there's a model. So we had it like that. So let's see if we can just use a function like linear SBR. Let's see how that one does. Oh, that looks nice. Oh, did I not run it? Because I hit stop. So this one's a little bit better. So we'll call this one like SBR, linear SBR. So this one's better, but it's actually still not as good as the linear regression one. So this one with the SBR, I got 34 and 51. So it's still like, you know, not as good, not as good. But I mean, it's all right. Don't get me wrong. If I got this model, even if I've never seen this one, I would be pretty happy with this. You can see that with our two little predictions that we did. Did we do good on those predictions? The two sample predictions that we do. Model predicts 2747, error 116. So let's see. I hard-coded the numbers, so yeah, it's all right. It's all right, but you know, kind of okay. I mean, could we tweak it? Could we improve it? We definitely could. Let's try changing the epsilon a little bit. So, okay, so now that we saw this one, I'll comment this one out. So let's try making this 0.1. And then how that will do. That did pretty bad. Yep. I mean, yeah, that's pretty bad. Okay, I'll do that. Let's do 1 and 1. Yeah, it's pretty weak. But hey, you're able to run it, so there's that. So yeah, I think that's pretty much all. I'll stop there for the regression one. Like I said, the vector machines are more, for classification. But don't get me wrong, we could probably get this probably as good as a linear one if we tweaked enough with the parameters. But like I said, I don't have time to do that right now, so we're just gonna move on. Okay, but you saw how easy it is to do it. We just import and run, like bam, done. Okay, so let's move on to the next type of algorithm. So that one is going to be decision trees. So decision trees, as the scikit-learn says conveniently right there, is that they are non-parametric supervised machine learning methods used for classification and regression. So we can use them again for both classification and regression. And I guess the simple way to understand it is think of like a quiz. When you want to find out if something belongs to one class or the other, you ask it a bunch of questions to the data, and based on what those answers are, it classifies it to one. And for regression, it's kind of the same thing. The cool thing about decision trees is that you can actually see the tree that's being built. And again, this all runs automatically. You're not actually having to come up with these questions. Some problems are better solved with decision trees than other ones. I guess you can read the pros and cons right here. There's a lot of them. The one that kind of pops up to me is this one, that decision trees can definitely handle multi-classes, multi-output problems. They're also efficient in their speed. Well, actually, that's more when we do the assembly. Yeah, so I'll take that back with the efficiency. They can be very nasty with overfitting, though. Overfitting becomes a problem with decision trees, so you have to be careful about that there. What else stands out from this? Well, I guess it can be visualized, as we'll see in a second. So there's that. Logarithmic for the cost, sure, because it's a tree. I guess this is a good point that they mentioned here, that the scikit-learn implementation of decision trees cannot handle categorical variables, just numerical variables, okay? So just be aware of that. However, know that you can do decision trees with categorical variables. You'll just have to look for a different library than scikit-learn. Disadvantages. Let's see anything important here that I would want to point out. Unstable. Yes, very unstable. So when you build a decision, so a lot of the times when you're doing machine learning, you build a model that works, but then you get more data down the line, and you want to see if you can maybe improve your model. So you feed it the new data that you found, right? You keep learning. Your model keeps improving over time. It becomes better and better. When you do some vector machine or like a logistic regression, and you add more data, it doesn't change the model much. Maybe it'll perfect it. Maybe it'll screw it up a little bit, but the changes are minor. Decision trees on the other side are very unstable, as it says there, and even a slight change in the input data can completely make a whole new different model, which might not do as well. And even if it does, it's inherently a completely different model, which could be good or bad. So as it says there, with assembly, which will be the next one we do look at, you can mitigate this problem, but it is definitely something to consider. Okay, there are also kind of kind of weird and the dark magic-y like when you're using them. So you have to be unless you really know in depth how they work, like they can just get really weird. So I think that's enough about that. Let's just go ahead and see how they work. And guess what? That's it right there. Well, actually, you got to import the tree and then call the function, and then you're good to go. Again, very easy to get up and going. Although, if you want to see the tree, you can use this right here. They actually have an example on the scikit-learn website for the iris data set. So I covered that in one of the videos. You can go back and take that code that you did and then try it out with this and get to see the iris data set being run with a decision tree. And they also talk about visualization and other tools you can use to visualize a decision tree. But this is actually a nice example of what the decision tree looks like for the iris data set. You can see how each of the questions is like a math question based on the size, on like the content of a certain feature. And it kind of decides on where to go in the tree. And when it gets to a branch, that's, or like a leaf node, sorry, when it gets to a leaf node, that's when it makes the decision. And that decision is which class it belongs to. You can see here that, it could be Virginica, Versicolor, or Setosa, which are the three classes, right? So I welcome you to try it on your own with the iris dataset, but we are just going to run it with the crypto dataset because that's the theme of the day, right? So let's again go from which one do we do? Let's start, I guess, with the let's do classification first. Yeah, let's use classification first, since we kind of went in that pattern doing classification first. So this one's going to be decision tree. Will it go up or down? So again, all we're going to do is we're going to go down to the, again, so I took this is the code from logistic regression video. And we're going to look for the line where we create the object. So instead, we're going to create a tree object. And instead of importing linear model, we import tree, happy trees. And then here, instead of using that, we use tree dot, and then decision tree classifier. I think that was the one. Decision tree classifier. That sounds right. Is that the one they use here too? Yep, that's the one they use there too. We can leave the random state. Let's get rid of the solver stuff. And then the one cool thing about this is that drawing of the tree. So let's actually go in and put that here. We do have to do that after the fit function is run. So just down here, I'm going to make a draw the tree. So for that, I'm just going to say tree dot plot tree and pass in the name of the variable, which is just the log reg. Okay, like that. So this will draw as a tree, which is pretty cool. It's going to be a massive, nasty tree right now. So we'll see. So run it. And it's running, it's processing. Give it a minute. While it's running, actually, let's, oh, my computer's like, you could hear it like spinning up the fans. So here we got some figures. So it's not looking too good because I see a bunch of stuff in the false positive and false negative categories. But check this out. Look at that. If I try to make it big, it's going to screw up. So I'm scared of doing that. Let's just leave it like that for now. But you can see the tree is definitely kind of not very even looking tree. You can see it's got more stuff on this side, I think, than this side. Can I zoom in without it breaking? Oh, ooh, it's like loading now. Oh no, hopefully it actually loads something. But even if we can't zoom in, you can see like right here, it splits, right? So it's a binary tree from the looks of it, because that's just kind of what it is. And then you can see, it asks questions, and eventually when you get to a leaf node, which could be as high as here, then it's like, okay, this is what the class it belongs to, which is to buy or not buy. Okay, so That's it's not wanting to zoom in. Maybe if I save the image. I'm scared of doing this. Let me try that. Please don't crash VM. It's a very, very big drawing, so that's why it's like struggling. We'll just put that to the side for now. And let's close this. Oh, look, it's slightly bigger now. We can almost not read it again. All right, we'll see if that works to zoom in. We'll let it do its thing. But let's actually look at the values of the precision and recall. This is when we'll know whether this fancy looking tree is actually useful or it's just for looks. So decision tree classification. Oh, I guess technically we should put this in the up here. Let's so I don't get confused. Put a line there. Okay. So for decision tree, oh, let's bring in the accuracy too. Here it is. So as fancy as our tree looks, the accuracy is actually lower. So we started with 77% for logistic. We saw SVM, kept the same accuracy, but you know, improved our precision at the cost of our recall. This one, interestingly enough, it kind of brought in a nice balance between precision and recall. They're both about 66%. So I guess there's an argument to be made that it makes it nice and even. But the accuracy is also low. It's like also like 66%, 67%. So I still think the logistic is the best one. Or actually, I think SPM is the best one that we gotten so far. But this one gives us the bonus of having a pretty cool picture that's drawn. So there's that. Did it actually finish zooming in? No, it just like, it gave up. That's okay. Yeah, I'm just gonna close it. I don't want this to crash. But yeah, we could you know, we could tweak the parameters to see if we could decrease the number of like the levels of the tree. I'd have to look at the parameters to do that, see where I can tweak with that. But yeah, I'll let you guys play with that. How about that? So we can move on. Yes. The good old, you know, I'll leave this as an exercise. All right. So let's move on. Let's do decision tree regression. Okay, so this one, by the way, it's on the same page here. So this was what we're doing. And if you scroll down further, and I will leave links to all of these in the description below. Oh, I must have passed it. So classification code, regression code. See, decision trees can also be applied for regression problems using the decision tree regressor class. Example, decision tree regressor. You can see that's it. Voila, you're good to go. And then the multi-output stuff that they were talking about, which is what trees are like, good for, decision trees. So let's go ahead and just do that. So tree, decision tree regressor. Let's keep a random state. It's good practice to do so. And then let's run it. Or actually, wait, no, let's also attempt to draw the tree. Or try to, at least. As we saw, it doesn't quite always cooperate with us, the picture. Tree.plot tree regression. The parameter of plot tree is basically the name of the model, so that's why I'm putting in that in there. Okay, I assumed you caught that, but just in case. Okay, let's run it. Definitely takes a little bit of time. Oh, darn it. We got to remove this coefficient line. So let's run it again. Doing some machine learning. And yep, it finished. Now it's just trying to plot it. While it decides if it wants to plot it or not, let's just copy these and compare it to what we got so far. So let's not get confused. We're looking at the regression category. So decision tree regression. So in this category, the linear regression has one so far. By the way, there's tons of different linear regression types. So like right now, it's indicating like I should just go and play with linear regression and tweak that rather than like try these. But still, this one's actually doing pretty good. Like the mean absolute error is definitely the lowest of the new ones. It's better than support vectors. Still, the linear regression one's giving us the better one. But this one's close. Like it's close. It's pretty good. Oh, I'm getting some scary stuff happening. Oh, it's the graphs are almost done. So yeah, it's not bad. I mean, I also think this one, if we tweak the parameters, although decision trees are very sensitive, I just tweak something and like the whole thing changes. But we could probably approach this and maybe surpass it if we. I think maybe. Anyways, let's see. Oof, that one looks scary. That one looks like a real, like one of those like tropical trees with a lot of leaves and branches. At the risk of this dying, let's just try to make it big. Oh no, that is a red flag right there. Okay. We'll just we'll let it do its thing. But for the few seconds that you saw the tree, you could see that it definitely looked more kind of balanced. And that's because of regression. You want it to be like looking like that. So yeah, okay. We're gonna put that to the side, and maybe it'll render it later. But yeah, so I think that's what I'll say about decision tree. So let's move on to the last one that I want to show you, and then maybe by then this will be finished rendering. So the last one I want to show you is going to be random forest. So let me bring that one in. So this is random forest classification. Also, you're able to do regression with it. So random forest is actually an algorithm that is known as an ensemble algorithm or ensemble learning. What is ensemble learning, you might ask? Well, let me tell you what ensemble learning is by giving you an example. So far we've done different machine learning models, and you might be thinking to yourself like, hey, like I like this algorithm and I like this algorithm. Couldn't we just like ask them all and then maybe take like a vote, a voting system, like make 10 different models and then like say, hey, rather than like picking one model and going with that one, why don't we bring them all in and then have like a consensus? That can work sometimes. Sometimes it's counterintuitive, but it doesn't do you better because you got to train them all, and that takes long, and it can be bad. But it's a good idea. Having a kind of a consensus is good because it sort of removes the risk of one model being completely wrong, right? So like, for example, with like rockets and things like that, instead of having like one altimeter, it will have like 5 altimeters, and then they're all measuring the altitude. And then instead of like just looking at one of them, the computer looks at all 5, and then sort of, you could say it takes the average of them, or it makes a decision based on like, what is the right altitude, right? If one of them completely shows like a completely different altitude, that would mess up the average. But like, if it just shows a completely off altitude, then it's like, hey, I'm going to ignore that one and go with the majority consensus. So that's the same idea behind ensemble learning, that you have multiple models and then you allow them to each kind of do their thing and then put them together and then make your final decision on what you want to predict. Specifically, random forest what it does is it makes multiple decision trees. And so by having all these multiple decision trees, then it goes in and makes the average of all of the output of all of them, and essentially gives you what is hopefully a better model. But like I said, ensemble learning is not just for decision trees. There's other, just whenever you're using more than one model, that is technically ensemble learning. Okay, puppy, go back there. All right. So here's the documentation for it. One cool thing about random forests is that if we're thinking about like the pros and cons of decision trees that I said, like advantages and disadvantages, is that each model is kind of its own thing. So you can train them parallel to each other. So you can parallelize. So like a lot of times when you're training these models, I mean, like other than like the decision tree, which took like more than a second to run, you're probably going to train them really fast, right? And I don't want you to think that that's always the case. In fact, it is definitely not the case. When you're training on real data, real models, it can take a long time to train them, okay? I'm talking about potentially months or more of training time. That's kind of the norm. So time becomes an issue. If you all of a sudden, because you're trying to do this ensemble learning, you gotta train 10 models instead of one, that's really bad. Now you're talking years if each one took months, right? Well, hold on a second. Each of the models you're training can be trained separate from each other independently. So I'm not saying this is easy, but like go get 10 computers like yours and then put on each computer one model and then train it. And in theory, that's kind of what parallelization is. You don't have to do it on different computers, but you don't get, most computers nowadays have multi-processors or multi-cores at least. And each core can be working on its own thing and you can speed things up. So making it parallelizable is a good thing because it speeds up your training, or at least there's no additional time training takes because you're doing ensemble. So there is that benefit in that. Another sort of pro that I can think of, I think there was something here I wanted to mention. I was looking at this earlier. Oh, well, here's this thing about this. We have our max depth parameter. That's what we want to tweak for the number of leaves. So I'm going to go back and tweak that in a minute here. But I guess also I'll say, yeah, also what I'll say about random forest. By the way, did this finish? Oh, it finished making it slightly bigger. So there you go. You can see that right there. Okay. Overfitting. Yeah, so decision trees are prone to potentially doing some nasty overfitting. The advantage of random forest and ensemble learning is that you can train specific features on specific trees. And so it helps to boost certain features that may otherwise be sort of overshadowed. So one of the big things that when you're training a model is you got a bunch of features, right? And some features may be important to train your model, but they might be too small. And you can do normalization and things like that to make them even. But even then, like, they might not be easy to have the model like actually give them enough weight. By essentially feeding only certain features to certain parts, so certain of the subtrees that you have in your random forest, they are able to sort of shine. And there's sort of a subcategory to this that I haven't mentioned at all, which is like ADA boost and all these things that you can use to sort of make those underrepresented features shine. But all those things kind of help random forest sort of have the best of decision trees, okay? So really, if you're going to use decision trees, you should also consider random forest as well, because there's no downside other than like more work, really. So yeah. So I think my dog wants to eat, so there we go. Okay, so yeah. All right. One last thing though, I wanted to mess around with is just try to decrease the Is this still decision trees? This is decision trees. Let's try to decrease the number of branches just so you can see the tree better. Max depth, let's just do like 10. Or no, let's do 5. Rerun it. There we go. This is way more viable now to look at. Come on, zoom in. Why won't you zoom in? Still won't let me zoom in. That's tragic. I don't know why it's so slow. But by the way, the fact that we lowered the number of by the way, the depth means the level of the tree per se. So like how many questions it has between the first node and like a leaf node. Interestingly enough, actually, the this was regression, right? Yeah, so the regression didn't go down too much. Like we did decrease it. So like before or we did make it worse. Like before we had a 28 mean absolute error and we had a 58 mean square error. Now it's slightly higher at 33 and 59. But the big advantage is like our tree depth went from like that massive tree to a much simpler tree, which means they're only asking me like 5 questions per se. That's much faster. You know, and much simpler model, which tells us that everything else is probably overfitting at that point. So there's that. So I apologize that the zooming in doesn't work, but you can still see it here. You know, this is what it kind of looks like. It asks questions to the features, and then based on those results, it decides where it goes in the tree and then makes a decision on what you're trying to predict. They do mention here, there is another library you can use other than this plot, which is called a GraphViz. You can import GraphViz and then use that. I don't know if I have it installed, but you can see here you can install it with Conda or pip. Probably have to do it with pip. You know, I will try that really fast. So pip install GraphViz. Okay, that installed rather quickly. That's a good sign. And then let's just try to let's just copy and paste what they have there for the graphing. So let's remove this graph. So we got import GraphViz, and then create export GraphViz. So I don't know what this dot data is, but I'm gonna leave the same variable name. This has to be my regression model. Out file none. Graph render iris. Okay. It's not called iris though. It's just gonna be called crypto. Okay, let's just see what happens. Failed to execute. Try one more time. Make sure the executables are in your path. So probably I need to tweak around the install to get it to work. So, well, there's that. Let me Google this really fast. It says to try to install it with sudo. Okay, we'll try sudo then. Is that the... Okay. That is taking a longer time to install, so maybe that's a good sign. Okay, that is installed now. Ooh, I got no error. Okay, so there's that graph. Okay, so maybe it did save it. Let's take a look. Crypto PDF. And there we go. So we did get something. It looks kind of squishy, but at least this one we can probably zoom in. Yay! We can zoom in. Why does it look so like wide? I don't know. So success. You know, never tried this library live and it got working, so I'm very happy there. Okay, so now you can finally see it. I mean, I guess that's just the way. I mean, it's trying. Obviously, it's trying to make the graph readable, so that's why it became this wide. But at least here it's a PDF, so like I could print this out in the massive poster, or I can just zoom in, which is what I want. So let's see it. So we got the true and the false, right? So the first question is asking at this specific column, so x2. So that's the third value. So what is that? Let's try to remember what that actually contains. So let's look at where are we feeding our features? This one. So this is 0, 1, this is 2. So I'm guessing this is the opening price. Okay? So the opening price is going to be x2. So the first question that the decision tree is asking is, and this is regression, right? We did this on regression. Yes, this is regression. So it's trying to predict the closing price of Ethereum. So the first question it asks is the price of Ethereum greater than or equal to 1,294? And if it is, then you go to the left. And if it's not, then you go to the right. Okay? So, and then you pass some of these values as well. So let's think about why I would ask that question. Well, you know, a certain time period, Ethereum was probably like, you know, a lot lower in value, so the increases were softer, right? But you know, if like Ethereum was $100 per ETH, if it went up in 10%, that's a $10 increase. That's a much smaller increase than like if it's 1,000 and it's a 10%, it's a $100 increase. So maybe that's kind of what this is asking, you know, like it's trying to kind of figure out where in the area is, and that's how it's going to predict it. Now that's completely me guessing. This could just be some weird math that it figure out that number is there. But as you can see, it's kind of weird. It's just like this is a very specific number it picked. So it's kind of spooky in a way. Let's say that it is the case, that it is smaller. You can see that the next thing it's asking is if it's smaller than the smaller number. True or false. If it's not, then it asks if it's a bigger number. Just keep going the true category. Now it's asking if it's even a smaller number. So it seems like it's asking if it's small, small, small. And then it's got this random question here, if it's smaller than this, which, it's looking at a different column. Okay. So now it's finally gotten to the point where it's asking if the Ethereum opening price was less than $139. Okay? At that point, it's going to now ask us, column 0, which is, I think, the Bitcoin opening price. Why did it get lost again? Here we go, opening price. So now it's asking us the opening price of Bitcoin. It's asking if it is less than 1,300. If it's less than, then you can see here, it's got a decision section, so it feeds it some data. If it's not, then it's got this decision area, so it feeds it some other data. Okay? So moving on, finally, to the last one, like I was talking about with ensemble learning. So let's start with ensemble learning for the, let's close some of these out. So this was support vector machines. Let's close those so we have space. Okay. So let's start with regression. Or here, classification. That's what we've been doing first, classification. Random forest, classification on crypto. And then one more. We'll leave this ready to go for the regression. Okay? So for the classification, we're going to change this to ensemble. Let's bring that one in. Where is it? Ensemble. So this one. So you can see the example code right here. Actually, oh, is it? It's not ensemble. It's just random forest. Yeah, it does seem like to be the case. I thought it was ensemble for some reason. Oh, I see. Ensemble is part of random forest. That's what it is. They don't show it here, but I'll show you. So if you don't see, if you just try to import random forest, it will give you an error. Oh, I see, because they're saying from scikit-learn.ensemble. So in the documentation, they're saying from scikit-learn ensemble. But I like to do what I've been doing so far. So from scikit-learn import, and they just say ensemble. And now if you want to use this, you can just say ensemble.random forest. But before that, take a look at all the other things that we have in here. If you want to understand the whole thing with the baggings, an ADA boost and all these things, you have to check out those separate videos. For now, I'm just going to show you this very basic random forest. Okay, so we're just going to go with the random forest classifier. Okay, so put it like that, run it, and let's see what we get. All right, we've got some results. Let's compare them with the other ones that we have. So here are our decision trees. And now we're going to put random forest. And remember, random forest is an ensemble in this case of the decision trees. And we can see that it actually did about the same as the decision tree, the individual decision tree. So there was no real improvement, and there's a reason for that. The random forests help you when you have many features, and like I said, some of them are not as strong, so they don't show, and you kind of boost them with this stuff. But we're only dealing with 3 features, and so there isn't much to do in terms of multiple trees because you have so few features. So I'm not necessarily surprised that it didn't do much better. Okay, if you had a lot of features, if you had like a model that we were feeding as your input a lot of features, then I think you would see an improvement in the random forest versus. And that does bring me to a topic about the curse of dimensionality that I want to bring up. But before I do that, let me show you the last one with the regression, random forest using regression, and then we'll talk about that. So, random forest regression. What's my dog doing? My dog's been really messing with me today. Okay. Ensemble.randomForest regressor. Okay, and I should be good to go. Oh, get rid of this coefficient thing. Okay, there's our model. It's pretty cool. And ooh, it has some potential. But it's not as good as we had hoped. So it's a little bit better. In this case, we actually had an improvement over the decision tree, the solo decision tree. Went from 28 to 22. Even though that could be, it could be as much as the dart situation kind of that I was talking about. It's a really small improvement, but it's an improvement nevertheless. I wouldn't just completely say, hey, that means this is better. Again, this could just be strictly like the randomization got you a little bit lucky. Like, let's try running this with a different random number. 52 seed. $22.46. That was slightly better, but still the 22 seems to be the pattern. Okay. So it's so close that like it's kind of risky to say that it's better, but it seems to be slightly better, at least for the regression than the solo decision tree. However, at the end of the day, for regression, the linear regression still beat them all. And I think that that's mostly due to the fact that it's you only got 3 features, and there's a correlation between them. That's the reason why we're doing this, to discover that. So I'm not at all surprised at the linear regression one here. I think you need some more complicated data, more features to be able to have these ones shine. Nevertheless, this considering the fact that the decision trees are a completely different way of doing things in linear regression, it's interesting that we got almost the same output, from just off the bat. So there's something nice to be said about that. So here we go. We got them all. We got, for the classification problem, we have 4 different things we tried. So support vector machines, decision trees, ensemble learning via random forest, and of course the original logistic regression. So we have 4 things. Sure, we tried 2 different ones for support vector machines, but still support vector machines. And we also have 4, because we did linear regression, support vector machines, decision trees, and random forest for regression. But you can see that the code is almost the same. We only were changing those 2 lines. We added a couple of extra lines for the decision tree because we wanted to see the tree. But you don't have to see the tree. That's just like something cool to see. So really, it's very easy to use the different models. And you should. Of course, I'm only showing you how to use them. You got to go in and tweak the parameters to try to get the best out of them and understand them as much as you can. As you can see, mostly I've focused on, with linear regression and logistic regression and then support vector machines, and not really, today's the first day that you see random forests and decision trees. But there's a lot of other tools out there. We just don't have time to talk about them. But you can see they're very easy to use. And then if you're interested, you see some good results, then you can read up on them further and get more information. So, yeah, That's kind of the main goal of this video, was to show you that. Now, the one thing I mentioned that I wanted to talk about was known as the curse of dimensionality. And so the curse of dimensionality, you know, because I'm saying, like, more features is better. And yes and no is the real answer to that. I do think that if we had more features, we could definitely improve our model, because think about it right now. Our model is trying to predict the Ethereum price by just looking at the Bitcoin price and the opening and close, and then the Ethereum opening price. There's no additional external factors there when we know that there's a lot of external factors that go into deciding the price of something. There could be news, like Elon Musk could tweet about Bitcoin and make it go up, or like there could be China or another country could like ban crypto, and that could make crypto crash that day. Or you could have just in general like financial information come out about something, or there could be a major hack, major loss of money for a certain crypto. And so there's a lot of external factors, right, that our model is not predicting at all. Like, it doesn't know. And so how could we improve our model? Well, we need to know that information. And so you say, okay, let's bring that in. How can we do that? We need to quantify all these things, but we could definitely quantify and say like what the feeling of Bitcoin and Ethereum is of the day based on certain factors. Like, you can do like natural language processing and other things. But at the end of the day, as you build more features, you run into another issue. And that issue is that you need to have the training data to support that. Here's the reason why. Suppose you have a piece of data. Forget about the crypto for a second, just data in general. And this data, it turns out that it's of different types. In fact, here, let me do different colors. And you're trying to linearly separate the data, right? And you heard me talk about like the kernel trick in other videos and things like that. But at the end of the day, when you're trying to separate this data, you could try looking at a higher dimension, right? And see if the data is separable. Okay, that's fair and it can work, but there's a catch to this. The higher the dimension you go, the more sparse the data is going to get, because if you think of each feature as a dimension, you're going to get to the point where you just don't have enough data in that dimension to actually be confident that it's actually the data itself that is saying this is separable, and not just the fact that you don't have the data for it. And so any data could be separable if you go high enough dimensions. But what you're really doing at that point is you're overfitting. And so that's what's really known as like the curse of dimensionality. That the higher you go on the dimension, trying to separate the data, the more data you really need to support that. Otherwise, all you're doing is overfitting. Okay? So unless you have enough data points on your data to be able to support that many features, it might actually be counterproductive to have more features to try to solve something. You might just be overfitting. And it'll look like it's working, but you're just overfitting it, and it's not really doing much. Okay? So I'll leave a link to an article on the curse of dimensionality. It has some pretty cool pictures showing you how, like, if you go to like 512th dimension, you can linearly separate data that otherwise wouldn't be linearly separable. But it's still kind of useless to you, because you're just, at that point, you just overfit everything. So I recommend you check it out, because it's one of those things that you have to be very aware of when you're doing classification, to make sure that you don't you don't just make a model that just overfitted everything and it's not really working. Okay? So yeah, I just wanted to bring that up, because as I was thinking earlier, I was like, this is something good to know about. But yeah, that's pretty much all I have for today. So you got to see this. I think this is going to be the last video that we do on the crypto data set. Maybe we revisit for neural networks, but at the end of the day, I think this data set has kind of reached its end because we definitely need more features for it to be useful. Even with the cursor dimensionality, I do think we need more. So there isn't much to see. And when you do something like neural networks, you'll see that it works also better with larger amount of features. One big thing I want to point out is that with the models that I've shown you so far, feature extraction and feature selection is very important. What features you feed your model matter, and you're in control of that, and it can affect how good your model performs because of that. As we move on to things like deep learning, you'll find out that that sort of human involvement goes away, and you no longer need to worry about that. The model will do that for you, which is pretty cool. Right now, you gotta say like, hey, I should feed it in like these features and not these features. With deep learning and the models that you'll see in, like later on, that's done automatically. The model knows, and that's pretty cool. So, however, that's not to say that what I'm showing you is just useless nowadays. There's still a very big use, and I encourage you to use it. So, keep it in mind next time you do a project, and looking forward to see what you come up with. So thank you all for watching, and I'll see you next time.